All right, so I'm I'm so sorry, apologize for being very late and delaying everything, but it's a great pleasure to have Yaodong Li as our speaker today. I've been very much looking forward to hearing about this work, which like many of us have been reading with great interest. So without further ado, please go ahead.
Okay, I'll start now. Can you hear me?
Clap, everybody. Can you hear?
Sorry. Yeah, thank you. Thank you for the. You can hear me, right?
Yes, we hear you.
Okay. Good afternoon, everyone. Thanks for the kind introduction. My name is Yaodong. I'm a graduate student from UCSB, and today I'll talk about a recent paper with my advisor, Matthew. There's a picture of him. The title is Robust Decoding, a Monitor Dynamics of Open Quantum Systems with Z2 Symmetry. So in this paper, we considered a decoding problem of quantum error correcting codes as motivated by the phases and phase transitions we found before in the so-called hybrid circuits as driven by the measurements. In particular, we want to show that the solution of a circuit can motivate new decoding algorithms for existing quantum error correcting codes. And these algorithms are interesting and in some cases are even preferable as compared to existing ones. But before I start, I want to thank the organizers, Una, Debanjan, and Chaoming, for giving me the opportunity of giving this talk. And yeah, please feel free to interrupt me with questions at any time. So the plan of this talk is pretty straightforward. I will first introduce the measurement-induced transition in hybrid circuits, and from there, I'll try to motivate the decoding problem in a particular model that can be exactly solved by mapping to a two-dimensional percolation problem. So I'll start with the hybrid circuit model as appropriate for hybrid Zoom meeting, I suppose. So this is a random circuit model in 1+1 space-time dimensions, as shown here. The gray boxes represent random unitary gates, and the unitaries will try to couple nearest neighbor qubits and increase the entanglement. In fact, if the unitaries are all you have, the circuit will almost always saturate to a state with maximal entanglement, and the entanglement entropy will scale as a volume of a subregion A. Now, in the hybrid circuit, the new ingredient is these single qubit measurements represented by these hollow circles in between the unitary layers. The idea is that an experimenter will be monitoring the circuit. He or she will be performing these measurements and record the measurement outcomes. In doing so, he or she will learn something about the state. And in this way, the state will remain pure after the measurement, if you started with a pure state. This is known as a quantum trajectory approach for describing open quantum system dynamics. But of course, in quantum mechanics, we know that a measurement does not only reveal something about the state itself, it also changes the state by collapsing the wave function, as shown here in this equation. So here, Pm is a projector onto the state labeled by the measurement outcome m, and I'm normalizing the state with a proper Born probability. So we really want to consider the many qubit. In this case, I want to consider the many qubit state that is being constantly coupled by the unitaries and collapsed by these measurements. And this leads to an interesting and non-trivial dynamics. I want to focus on the quantum trajectories, as I said, as labeled by the measurement results. And I'll be focusing on the entanglement properties of the state at long times or in a steady state. So what we found is a phase transition as you increase the rate of the measurement. The idea of the measurement-induced phase transition is as follows. There are two possible dynamical phases in this circuit when you have strong measurements when P is large, or weak measurements when P is small. In the limit, when P is large, you're effectively measuring each qubit at each time step by projecting into by projecting it into a spin up or spin down state, for example. And in this case, the state can never develop an entanglement larger than an area law in a system size. On the other hand, if you do not have any measurements, as I said, the unitaries alone will scramble the information across the system, and the entropy will scale like a volume law. In this case, in a one-dimensional system, S will be linear in the subsystem size L of A. And here is a schematic, here's the phase diagram, and here's a schematic illustration of the scaling of the entanglement entropy in the two phases and at the critical point. So we access this transition mostly numerically in a special type of circuits called Clifford circuits, where the gates are chosen to be the so-called Clifford unitaries and the measurements are chosen to be Pauli measurements. And in this case, we can perform large-scale numerical simulations of up to hundreds and thousands of qubits, and we can get pretty good data in the two phases across the transition. And here I'm showing the mutual information between two disjoint regions, A and B. And as I cross the transition, I see the mutual information sharpens up as a function of P with increasing system sizes. And this is indicative of a divergent correlation length at the critical point. And this follows a usual finite size scaling formula near the critical point. The critical point is particularly interesting, but I also want to point out that the volume law phase is also a bit unusual. Besides the leading volume law piece in the entropy, there's a sublinear power law piece, LA to the power beta, where beta takes a value close to 0.3, between 0.3 and 0.4. So I'll come back to this shortly after. At the critical point, I can vary, as I mentioned before, I looked at the mutual information between two disjoint regions, A and B, fixing the sizes of A and B to be proportional to the system size. But I can also vary the endpoints of A and B. There are 4 endpoints, X1, X2, X3, and X4. And the mutual information collapses nicely, fits nicely to a function of the so-called cross ratio. And this is usually regarded as an evidence for conformal invariance at the critical point, and is suggestive. And this result suggests an underlying CFT. The CFT, of course, describes the universality class of this phase transition, but this is a very complicated CFT whose nature hasn't been understood and is an open problem at this moment. I'll also talk briefly about the volume law phase, which is also pretty interesting. As I mentioned, the volume law phase is a bit unusual, as characterized by a linear plus sublinear form in the subsystem entropy. It is interesting because initially it was a bit surprising. People would have thought that the entropy is something fragile and it cannot survive. And in particular, volume law entropy cannot survive as long as some finite density of measurement is present in the circuit. However, it was realized by these authors after the transition was found that the volume law can be understood as a dynamical quantum memory or dynamical quantum error correcting code, and it illustrates the principle of quantum error correction. The idea is that when the random unitaries are prevalent, they can scramble the information and hide it non-locally across the system in a way that is inaccessible to local measurements. So this is just like in a quantum error correcting code. You can lose a few qubits without losing the encoded information, because the information is not encoded on any of the individual qubits, but encoded throughout the system. If this picture is correct, this suggests that this circuit generates a quantum error correcting code with a large code distance, at least larger than 1. And the circuit can be thought of as an encoding procedure of that error correcting code. Later, it was realized that this code properties of this code can be understood conveniently in a picture with fluctuating entanglement domain walls that follows from a mapping to a statistical mechanics model. So in this statistical mechanics model, the entropy of a subregion A maps to a free energy of a spin model. You can think of these as Ising spins. And in order to calculate, the free energy is defined as follows. So the qubits will live on the upper boundary of the circuit or the spin model. And this is a subregion A. In the subregion A, I'm fixing all the spins to be pointing down and all the spins outside to be pointing up. And in order to satisfy this boundary condition change, a domain wall in the bulk must be introduced, as I illustrate here. In the low temperature ordered phase of the spin model, the domain wall will have a finite, will cost the finite energy per unit length, and that's corresponding to the finite entropy density S0 in the volume law phase. And in addition, if you assume there's some quenched disorder in the bulk, the domain wall will be pinned by these disorders, and therefore the disorder introduces some fluctuation in the domain walls, and that will give you this power law behavior in the subleading term. This picture can also be used to calculate the code distance, which is characterizing how many qubits you can lose before you start to lose the quantum information of the code. And the code distance follows the same power law as L to the beta. So these are all very nice and pretty general, but this is very far from the full story. Other than these random circuits, either Clifford circuits or Haar circuits, there's been a lot of efforts in extending a similar phenomena in similar models with measurements, with or without unitaries. In the most dramatic case, there's this class of measurement-only circuits. The idea is that you do not have any explicit unitaries in the circuit, but instead measurements on a few, say 3 qubits. And these measurements alone can already generate a rich phase diagram and transitions between an error law phase and another error law phase, or between an error law phase and a volume law phase. There's also been—
This is a question. Is this like not a local measurement in a sense now because you're measuring 3 qubits?
It's still local as long as the measurement is supported on a finite number of qubits with a finite range.
Mm-hmm. Okay.
But you can think of it as a 3-qubit measurement as
Right.
a single qubit measurement conjugated by 3-qubit gates, unitary gates.
Right.
And in that way, it's
So it's
perhaps
kind of acting like, entangling the 3 qubit. It's giving that further rangeness, right?
yes,
Like,
yes, yes,
Yeah. Okay.
yes. In fact, this class of model is very rich, and the phases and the phase transitions, the critical properties of the phase transitions depend on which gates you choose, and it's not been understood yet. So this class of model is very rich, and there's also another type of enrichment that's appearing in non-unitary free fermion dynamics. In particular, I want to highlight this paper by Chalming and Andreas Ludwig and Bellabauer and Kesselman, where they show that depending on the symmetry classification of disordered fermions, there can be different critical properties of these non-unitary fermion dynamics. But of course, in these circuits, there's not a volume law phase, but usually you have a critically entangled phase with logarithmic entropy and an error law entangled phase. Most recently, there's been a paper from Ehud Altman's group, which proposes symmetry enriched phases in random quantum circuits. The idea is to consider the non-unitary dynamics as generated by some effective Hamiltonian and study the ground state of the Hamiltonian. By looking at a particular finite replica index, they found that the effective Hamiltonian has an enlarged symmetry as compared to the physical symmetry of the circuit, and there's a rich phase diagram that they explored. More recently, there's a paper from Roman Vasseur's group on random unitary circuits with U1 symmetric dynamics. There, in addition to the volume law to area law transition, there's a so-called charge sharpening transition that's separate from the measurement, from the entanglement transition. The idea is that if you start with a state without a definite charge, so there's some uncertainty in the charge, when you're making the measurements frequent enough, the charge, it will quickly collapse into a sector with a definite charge. So this is a charge sharp phase. And if you're not making the measurements frequent enough, there's still going to be some uncertainty in the charge. I think there'll be a talk by Utkarsh in a few weeks, so it'll be interesting to hear about. So yeah, I'm just illustrating the rich phenomenology in this type of dynamics. But in this talk, I'm going to focus mainly on the measurement only circuits, and in fact, the simplest example that can be solved. So the example is what we call a ZZX circuit with two types of competing measurements that can stabilize different quantum phases. So this the circuit is illustrated here. Nearest neighbors are coupled by the ZZ measurements, and single qubit X measurements are in between these ZZ measurements. These measurements are performed at a rate PZZ and PX respectively. And you can see there's a global Z2 symmetry defined by the product of X's on all the sides, respected by both type of gates. And the nice thing about this circuit is that in addition to the entanglement, there's an additional order parameter, Edwards-Anderson order parameter that can be used to probe the transition. It is defined as the spin-spin correlation function connected part of the spin-spin correlation function squared and summed over size and divided by the system size. So when the ZZ measurements dominate over the X measurements, there's a spin glass phase where the Edwards-Anderson order parameter diverges linearly in the system size, whereas in the phase where PZZ is smaller than PX, the Edwards-Anderson order parameter goes like a constant. So this is an order parameter in addition to entanglement, which might be easier to probe in the experiments. So in between these phases.
Question, do they show the same critical point, entanglement and the Edwards-Anderson? Is it obvious that they must?
It's not obvious, but I'll talk about the mapping, which makes it obvious.
Okay.
And at the critical point, entanglement is logarithmic. Okay. So yeah, so I'm talking about, so as I said, this model can be solved by mapping to a percolation transition. So in this case, I'm considering a two-dimensional square lattice where ZZ gates, ZZ measurements map to horizontal connected bonds, and X measurements map to broken vertical bonds. And accordingly, the absence of a ZZ measurement corresponds to a broken horizontal bond, and the absence of an X measurement corresponds to a connected vertical bond. And so the transition in the circuit is mapped to a two-dimensional percolation transition, and the spin glass phase and the paramagnetic phase will be the percolating and non-percolating phase of the connected bonds in this two-dimensional lattice correspondingly. And therefore, it's no surprise that the transition happens at the point where these two values are equal. As you probably know, on the square lattice, the percolation threshold is at 1/2. So when the two types of bonds are equal, occur at equal probability. And because it's exactly solvable, a lot is known about the critical properties. For example, the Edwards-Anderson order parameter as a critical vanishing with the power law that can be calculated from the percolation physics. There's an intriguing interpretation of this circuit as proposed in this paper, that if you draw the cluster boundaries of the connected clusters in the percolation problem, they can be viewed as the world lines of non-interacting Majorana fermions, and the Z2 symmetry I imposed on the system will become a fermion parity symmetry, which is quite natural in this setting. So, however, this is just a simple example of the possible phases and phase transitions that can occur in such circuits. These are all very nice, and they're interesting to theorists, but it would be even more interesting if we can probe some of these phases in the lab, as I'll discuss next. So I want to emphasize that the monitor dynamics is a special type of open system dynamics. It involves an active classical observer who takes down the measurement results, and the transition only happens on the level of the quantum trajectories. And this should be compared with the usual Lindblad approach in describing open system dynamics in terms of mixed state density matrices, the decoherence, which involves some decoherence. So in this case, the decoherence acting on the density matrix can be thought of as a measurement whose outcomes are forgotten. So if we forget about the measurement results, we lose the measurement, we lose the measurement-driven transition that would have occurred on the trajectory level. The reason for this is, of course, that for the density matrix, you can only calculate linear functions of the state, whereas the entanglement or the Edwards-Anderson order parameter that I introduced earlier are nonlinear functions of the trajectories of the states, and you wouldn't be able to access them without the measurement outcomes labeling the trajectories. So naively, there's an intrinsic difficulty in experimentally accessing the transition in general. For example, in order to compute the average entanglement entropy or mutual information of the squared correlation function, as I said, you need to compute some nonlinear function of the state. And in this case, it is necessary to have several copies of the same pure state wave function or the same trajectory psi. And this can only be achieved by post-selecting on a total number of L times T measurement outcomes, because you're making them at a constant rate. But quantum measurement outcomes are intrinsically random, as you know, from quantum mechanics, and cannot be forced. There are a number of exponentially many possible sequences of measurement outcomes. And you have to perform many runs of the same circuit until a particular sequence of the measurements appears twice. If you have one measurement outcome that's different, you get two different states in general, and you wouldn't be computing what you wanted to compute, or you wouldn't be measuring what you wanted to measure. So this looks like an intrinsic difficulty, but they're also being. Sure.
Is it possible to prepare an state, and like because you could theoretically, like you would say, well, I know, like I ran this set of outcomes, then I could try to start from the middle or somewhere close to the end and try to get just the end of the sequence. Is that a possible?
That's still going to be exponential in a number of time times the system size.
Right, but could you limit yourself to very
very
preparing this? Yeah.
You mean very shallow circuits?
Yeah.
Yeah, that's also possible. That's also one proposal. Thanks for the question. I didn't mention that, but because the transition is a two-dimensional transition, you should be able to see it in a thin strip if you want. That's another possible route of seeing the transition in the experiments, but it's still going to be exponential in system size L. Now you've taken T to be finite, right?
And do you need the system, like, do you need to do finite scaling or something? Like, do you need large systems to see the transition?
Moderate systems, I think.
What is moderate?
Like in the experiment, I'm going to briefly mention,
okay.
they have 6 qubits or 10 qubits ion trap, so they'll already see the transition.
Oh, cool.
So yeah, that's a nice question. Thank you. As I said, there have been proposals for addressing this challenge by considering special types of circuits. So the idea is, rather than considering the problem in full generality, you can look at special cases, in which case you might hope to overcome this difficulty. So a special type, one example is the so-called Clifford circuits that we use in numerical simulation. And this can be accessed using a local probe as proposed by Gollins and Hughes. So the idea is that different trajectories are labeled by different measurement outcomes can be related by a unitary which you can compute. And in this way, you can reproduce the same state without doing the post-selection, but by applying that unitary. So this is recently observed in an experiment on an ion trap quantum computer with 6 to 10 ions, I think. So this is a very impressive experiment, I would say. Another approach is to focus on space-time duals of unitary dynamics. And to access the transition, you only have to simulate the unitary site or in a quantum computer, which does not require any post-selection whatsoever. But after you perform the space-time dual, it will look like a unitary plus measurement circuit. This is proposed in these papers by these authors. This space-time dual idea is also related to a phase transition in the computational hardness of simulating 2D finite depth unitary circuit, as proposed by a group of computer scientists. In this talk, I'm going to talk about a third approach, possibly, of making some relevance of this transition by utilizing the measurement results in measurement protected phases. Actually, the one measurement protected phase I just talked about, the spin glass phase, to perform some useful decoding tasks. And in particular, I'll argue that the solution of the model motivates new decoding algorithms for quantum error correcting codes. So in order to do that, let me introduce the simplest possible quantum error correcting code, namely the repetition code. Here I'm showing the repetition code on 6 qubits, but this is just for convenience. You can have any number of qubits you want. The 6 qubit Hilbert space is 64 dimensional, but the code is only defined on the subspace of that full Hilbert space, a 2-dimensional code space actually, defined by the conditions that the nearest neighbors, the ZZ operator on nearest neighbors must have the eigenvalue 1 on the code space. As you can see, the code space is 2-dimensional, and hence it encodes 1 logical qubit, just like a normal qubit is 2-dimensional, and has a basis, and it has 2 basis states, namely the all 0 state or the all 1 state. A code state would be an arbitrary superposition of these 2, alpha 0 plus beta 1, with an arbitrary pair of complex numbers alpha and beta. An encoding procedure would be encoding a 1 qubit state, 0 and 1, into this 6 qubit state, 0 and 1, both faces. The encoded information would be the ordered pair of the complex numbers alpha beta that is in general only known to the encoder or someone who prepared this small size state, but unknown to us. And the question is, given the encoded state, how well you can preserve that information without knowing it or disturbing it, which in this case is the same thing. So I'll give a toy example of fault tolerance or decoding the repetition code with some errors on it, but in just one time step. So consider the initial state I just said, alpha 0s plus beta 1s. And I consider a bit flip error on the third qubit as realized by a Pauli X operator on the third qubit X of 3. And the resultant state is of course this. Now I want to I want to guess what the error is without disturbing the state. And the way to do that, as is well known in quantum information theory, is by measuring the check operators or the ZZ operators, and we find a syndrome. In this case, we measure Z1, Z2, we find +1, Z4, Z5, we find +1, and Z5, Z3, Z5, Z6, we find +1. But Z3, Z4, and Z3, Z4, and Z2, Z3 will be -1. In this case, we see that all the Z operators involving 3 has changed sign, but those do not involve 3 do not change sign. So we can guess, in this case correctly, that a bit flip error has occurred on the third qubit. In this case, and if we have guessed this correctly, we can apply the X3 operator back and recover the initial state. In one time step, actually, this guess will be correct as long as fewer than L/2, half of the qubits have been flipped. It is important to notice that measuring the check operators or the ZZ operators does not change the state, nor does it destruct the quantum information, namely the order pair alpha and beta. In fact, if you look at the psi1 state, this error state, measuring it's an eigenstate of the ZZ operators, and measuring it does not collapse the state or change the state in any way. Next, I'll consider a different type of error, namely a phase error, as realized by a Z3 Pauli operator on the third qubit. In this case, it will not change the basis states, but the sign between the two terms will be flipped. So previously it's a plus sign, and now it's a minus sign, because a 0 would give you +1 and 1 would give you -1. In this case, if I measure the check operators, well, I'll have all +1s, and I will conclude incorrectly that no error has occurred. In this case, we say that the error detection and correction has failed. So to conclude, the repetition code can be used to protect against bit flip errors, but not phase errors. And some people would say it's not really a quantum memory, but rather a classical memory. However, I want to impose a global Z2 symmetry X throughout the dynamics, so that the phase error, which is anti-commuting with the symmetry, would not be allowed. So it can also be thought of as a symmetry protected quantum memory.
How would you implement symmetry constraint?
It's just imposed by hand. Like, let's say this is
In
what I
in
want
a
to.
physical system, like you're interested in trying to do this experimentally, right?
Yeah, I'm not so familiar with the Majorana physics, but perhaps fermion parity symmetry is a good one. Or there are certain systems with bias noise, for example, in superconducting qubits, that maybe X errors are more popular than Z errors, in which case there's some approximate Z2 symmetry that can be used. Anyway, this is up until now, this is just a theoretical assumption. But later I'll discuss the case of Tori codes, which can correct both bit and phase errors. So this is just by way of illustration for simplicity, let's say. And this is because it's simple. This is what we understand the most at the moment. So with this decoding story in one time step, I want to generalize it into a time duration that's proportional to the number of qubits. So in this case, I want to view the ZZX circuit as undergoing errors and check operator measurements in this way. So the X measurements, I'll view them as Z2 symmetric errors with a rate P of X. And the ZZ measurements, I'll view them as check operator measurements, just as I did before, but now with a rate PZZ, which is in general smaller than 1. I want the circuit depth to be proportional to the system size. The initial state is the encoded alpha 0 plus beta 1 state, where alpha beta are arbitrary. And the question is, can we recover the initial state after the error has accumulated in a time proportional to the system size, just as in the previous toy example, where t is equal to 1. So this was a question I think first addressed in this famous paper by Denise, Kitaev, Landau, and Preskill in topological quantum memory, which is very famous, where they consider these the errors in that model is by replacing the X measurements by X unitaries. But here I want to be slightly more general. I want to generalize to any type of Z2 symmetric errors. Namely, it can be a measurement, it can be a bit flip unitary, or it can be a dephasing channel, which is truly a quantum channel. I'll focus on the first case, but the result really applies regardless of which type of Z2 symmetric errors you have. These errors do not even have to be, Clifford. So they can be pretty general as long as it respects Z2 symmetry. So it's a truly monitored and open system, but the open is due to the decoherence. And this is I want to contrast it with random circuits where decoherence in a circuit is a relevant perturbation. It acts like a magnetic field and it destroys the phases in the phase transition completely. So with Z2 symmetry, you can introduce some decoherence into the circuit without but still keeping the spin glass phase, for example. So before asking what we can recover, whether we can recover that information in practice, I want to see if that's possible in principle. So it was noted in this paper by Lan and Buchler that if you're in the percolating phase, where the bonds are percolating, the final state after you measure all the check operators will still have that information. And the state will look like alpha m plus beta m bar, where m is a bit string. And in this case, you just need to, the information survives, and you just need to infer what m is from the circuit history. And in the other case, in the non-percolating phase, they've shown that the final state will be a symmetric superposition of m and m bar. And in which case, the alpha beta is not even in the state. So there's nothing you can do. This information is irretrievably lost.
Yaodong, a quick question. So when you write m, it's some state that depends on the measurement record. Is that right? But
it depends on the measure. It depends on the measurement record. Right. Exactly. So next, I'll describe how you infer m from the measurement record. Yeah, I'll focus on the phase where delta p, so the percolating phase. And because I measured all the check operators on the last time step, I'll know the relative signs of m's for each pair of sites essentially, and I can recover the information as long as I know any m on any site v. from the measurement history. And in this case, I'll call the decoding is successful. And we show in our paper that when the measurement locations are known, so when you know which bonds are broken, you can find an error avoiding path pi from the bottom to the top that ends at site V, in which case the M can be inferred from the product of the measurement results on horizontal bonds along this path. And it's important to notice that there can be exponentially many such paths from a site V to the bottom, but all these paths will contribute the same sign, -1 to the MV. So this is a quantity I call Z cumulative on the path pi. So this, in this case, with located errors, when I know which bonds are broken, the spin glass phase equals the percolating phase and equals a decodable phase, as shown in this phase diagram.
But Yaodong, just to make sure, quick question. So the M sub nu is really just the measurement outcome that labels the quantum trajectory. I don't need to do a final state check again, or you need that as well.
Well, you do not need a final state check operator if the errors are ZX measurements. But if you have channels in general, the state can be mixed, and you need to perform those measurements in order to go back or near a pure state.
Oh, so I do need the history and some final check.
State measurements, yes, I'm assuming those, the ability to perform those.
I see.
Yeah, but yeah, I'll talk about a more realistic situation perhaps. But in this case, we see that the spin glass phase coincides with the decodable phase of the repetition code when the locations of the errors are known, but without knowing what the error gates are. Remember, I said that error gates can be quite general. And next, I'll consider a more realistic error model, assuming the locations of the errors are unknown. In real systems, of course, the errors are silent, and you wouldn't be able to know where the errors are unless you estimate from the syndrome measurements, or else the decoding algorithm does not depend on an explicit knowledge of the locations. So what if we do not know the location of the errors? So the idea would be to sum over all these good paths, spanning paths, without, in fact, some of them will be good and some of them will be bad. But as I said, there are exponentially many such good paths, and they all contribute the same sign. So by summing them over, you might hope to get a correct estimate of -1 to the power MV from the sign of this sum. So in this case, the good path will act as a signal, and the bad path will act like a noise. So the question is, can signal beat noise? Well, maybe in the percolate, as I said, the number of good paths is exponential in the system size. So in order to do some numerics, sorry, is there a question? Okay. In order to do some numerics, I want to be even more general with my error model. I want to allow some measurement results in the circuit board to be faulty, namely that due to maybe some measurements are imperfect, and the readout of a ZZ measurement can be the opposite of the value of ZZ on that stage. And we'll assume that the error rate per qubit, that's like the X errors, and the fault rate per qubit per measurement are the same, just for simplicity. So I have a two-dimensional phase diagram. The result I found by looking at the success probability of decoding, namely when sign of F is equal to -1 to the MV, is as follows. So I still have the parametric and spin glass phases defined without referring to the decoding problem. And previously, the decodable phase, which coincides with the spin glass phase, shrinks to a line. So in this case, there's not a finite threshold at any value of PZZ. Here I'm showing numerical data. Actually, different lines correspond to different system sizes. As you can see, increasing the system size, increasing the system size, you have a smaller and smaller success probability of decoding, but they also they cross at the percolation transition from 1/2 to 0. And this is when you have some information in principle, and this is when you do not have that information at all. This is the result for this naive simple decoder. in 1+1 dimensions. We can also investigate the case in 2+1 dimensions. And in this case, well, the model is similar to the previous one. You measure the ZZ operators at some time step, and in between these ZZ measurements, you have these errors, Z2 symmetric errors. And in this case, I do find a finite decoding phase, which is a subphase of the spin glass phase. So the spin glass phase becomes a necessary condition for successful decoding. And this is the numerical plot of the near the transition, where I find a critical exponent different from the percolation transition, suggesting that it's in a different universality class that may not be related to the percolation transition in 3D. Well, this idea, it will be nice if we can also correct both bit flip and phase errors, as we discussed in the we also explored the physics of the toric code in 2+1 dimensions, where the error avoiding path are replaced by error avoiding membranes. But in this case, there are so many membranes that I cannot efficiently sum over, and the decodable phase decodable phase disappears to just one line as well. So there's no finite error threshold. So this is the situation of the results when we posted the paper. So we can compare this result with a previously known method, minimal weight perfect matching, which is basically a maximal likelihood decoding. It tries to estimate the error history with the maximal probability. Of course, that is much more time consuming than our code, as you can see. In particular, in 2+1D for the repetition code, the matching problem is NP hard, where this decoder runs in a polynomial time. And in this case, we have a finite error threshold, whereas matching gives a 0 threshold. In the case of a 1+1D repetition code and the 2+1D toric code, our work gives a 0 threshold, and the matching does give a finite error threshold. After we posted the paper, we realized that our decoder, our naive decoder, can be improved. So this will be a version 2. So there'll be a slightly increased time complexity for the 1+1D repetition code, as well as for the 2+1D toric code. But in the first case, we have a finite error threshold. And in the second case, well, this is still ongoing. We do not know what the situation is. So I think in 1+1D and 2+1D for the repetition code, the algorithm as motivated by the percolation physics is preferable in some situations as compared to the matching, to the existing method in these two papers by Presco. So I don't think I'll have time to discuss the physics of the decoder in our upcoming version 2, but I'll mention that it's by relating the summing over path problem to a calculation of a correlation function, spin correlation function on the top and on the boundary in a random Bond Ising model. And in a random Bond Ising model, it is known that when the disorder is small enough, the disorder is like our error rate here. And when the temperature is low enough, there's a ferromagnetic phase. And the idea will be to magnetizing the lower boundary, which is like encoding an initial state. You'll be you will also be able to magnetize the upper boundary in the ferromagnetic phase, and in which case you can read off the encoded information. And this is a plot of the success probability for the improved decoder.
I'm a little confused. I thought your two-dimensional drawings were like 1+1. Am I right?
Right.
Yeah. So then, what is the role, and what sets the temperature? That 1+1, one was the time, and the other one was the physical dimension, 1D system, right?
Yes. Yes.
So what's the right temperature that I should think about when I make that 1+1 equals 2+0 mapping to the problem?
Yeah, the time becomes another spatial dimension.
Right. So the temperature is there still a meaning of temperature in your quantum circuit?
So the temperature is a parameter I can choose in order to do my Monte Carlo. So if I choose it low enough, I'll be in the ferromagnetic phase. And yeah, this is of course the situation I would like to be in. Whereas in the Pesco paper, they also map to some random Bourne-Ising model. In that case, temperature is related to P. It's restricted on this Nishimori line. So the two mappings, the two methods are slightly different.
So you're saying when you want to simulate the quantum system and quantum dynamics, you will set the temperature depending on what kind of quantum system that you want to simulate? Like, how do I relate to like physical experiment in the lab? If somebody does experiment in the lab, like what temperature should I choose?
It's not related to the physical temperature of the experiment.
Right. Then how would I choose which temperature to what to set the temperature in comparing to the StatMech model?
The temperature is arbitrary, as I said.
Okay.
I guess one way to put it is that, for example, the temperature is related to the error rate, like P, or some other parameter of the dynamical system. It's not the literal temperature.
Yeah, I understand. So I understand it's not the literal temperature of the lab. I'm trying to figure out like how would I know what
Right?
yeah. How would I simulate that?
You would want to choose it as low as possible so that the order is stable, but not too low such that your Monte Carlo does not equilibrate.
Okay.
But yeah, but in this
yeah. Okay.
Yeah, sure. Sorry, but in this random Bourne-Ising model, there the correlation function signals a decoding transition, and the decoding transition can be in 3 different universality classes depending on the temperature you choose. If you choose it to be falling on the Nishimori line, you'll be seeing exponents controlled by this fixed point. Whereas if you're below or above this temperature, you'll be either seeing the exponents for the disordered fixed point or the clean fixed point. So there can be different. We think there can be different universality classes of the decoding transition. But this is really some detail. I cannot explain this very well, but the result is in this table. By relating the sum over path decoder to a correlation function in a random Bourne-Ising model, I can achieve a finite error threshold for the repetition encoding 1+1D as well as for 2+1D. So to summarize, we started from the simplest measurement-only model, explored the associated decoding problem of the simplest error correcting code, namely the repetition encode in 1+1 and 2+1 dimension. With located errors and perfect measurements, the percolating phase coincides with the decoding phase, and this result can be generalized to toric code in 2+1 dimensions if you know the locations of the errors. With unlocated errors and faulty measurements, the decoding phase is in general smaller than the percolating phase, and with a naive path summing decoder and a more sophisticated one, we find finite error threshold for the repetition code in 1+1 and 2+1 dimensions. Here, the percolating phase is necessary, so it provides the spatial dimension d+1 for the StatMech model. If not percolating the space dimension, the spatial dimension of the underlying StatMech model will be smaller, and you won't have the ferromagnetic phase. There are some open questions, for example, different universality classes of the decoding transition, depending on the temperature and the disorder, as I just mentioned. And the toric code, one can also wonder whether the toric code can be decoded in a similar fashion by computing some correlation function in a random plaquette gauge model. However, in gauge theory, local order parameters are expected to vanish. So this is something we haven't figured out how to do. Some new techniques are needed in order to perform this decoding. It may be fundamentally impossible. It is also interesting to explore other types of hybrid or non-unitary dynamics and whether they suggest new codes other than the repetition code or the toric code. These have to do with the Z2 symmetry or the Z2 gauge field in hybrid dynamics. But the more general class of hybrid non-unitary measurement-only dynamics can be inspirations to new codes. A possible example would be possibly relevant. I don't know if this is really relevant, would be a flockade code by Hastings and Haar in the recent paper. And also ultimately want to connect back to the measurement-driven volume law to area law transition. And we're wondering what we can say about the decoding complexity of the dynamically generated code in the volume law phase. The keyword here is robust. That is, we need to work with silent errors, and we want to catch them. This is believed to be hard, but it hasn't been seriously examined. So this is an open question as well. And there are many other questions, which I'll not list. So yeah, that's all. Thank you. Thank you for your attention.
Thank you.
Yeah, I'm happy to take questions if there are any. Sorry.
So I have one question. The room is currently silent. So you know, somewhere back, you set up this problem statement that the post-election is very, you know, impossible. So does that mean experiment is impossible? And that kind of made me think that you're going to overcome post-selection problem, but then it looks like the target just changed to decoding problem. Did I miss something?
Oh, the post-selection can be thought of sort of a decoding. It's a brute force decoding. So you decode by performing the measurements many times until you match.
Right,
So
right.
that's one possible. That's a well-known protocol for example, random stabilizer codes. Without any structure, that in that case only this type of brute force decoding is possible. So yeah, this post-selection problem can be thought of as a decoding problem, although it's much harder than the Z2 case that I discussed. So we're really here trying to find examples which you can say something meaningful.
I see. So the sort of rationale is post-selection is a very difficult problem, but it is a type of, it's an extreme version of decoding problem. So you're going to target a sort of a much more manageable decoding problem.
Yes, or start from there as a first step. Yes,
Yeah?
exactly.
Okay. All right. Cool. Very cool. Any questions? Any other questions? No? Yeah, looks like there aren't any questions. I have more questions, but I don't want to subject the whole group to this. So I'm going to ping you because I have some ideas that I want to discuss. So it'd be great if you can talk more some other time.
I can stay.
We'll try to schedule a meeting separately because I have to run. There are other people with meetings.
Oh,
so,
okay.
Yeah.
Okay.
So let's talk sometime next week if possible. Okay.
Sure. Next week will be.
We'll schedule by email. We'll schedule by email.
Yeah, sure. Next week, I'm just saying next week I'll be in Santa Barbara, so Matthew can join as well.
Oh, you're not in Santa Barbara right now?
Yeah, now I'm not in Santa Barbara. Next week I will. So.
Okay.
Hopefully
right.
we can.
Yeah. So then maybe we'll all talk together. That'd be great.
Sure.
All right. Well, thank you so much. This was
Thank
very
you.
interesting.
No.
Yeah.
Thank you. See you. I'm going to stop share.